Hi, Hillary.
Hello, can you hear me?
Yes, I can hear you. How are you doing?
I'm doing very well, thank you. How are you?
Oh, I'm doing fantastic as well.
Great.
Yes. Sorry, I'm
Okay,
late. What
I
time
think
is?
we'll get started. No, it's okay. Yeah, it's okay. Okay, so I think we'll get started now. We have a few of us here: Karim, Henry, Iyanoloa, Crispy, Victoria, Isa. We're happy to have all of you here with us at this IPFS Africa community meetup. Something to note though, as we start, is that we're trying to get a subscription for Zoom, but we couldn't get it. So we have a 40-minute time limit for the meeting. So it's possible that the meeting cuts off at some point, and then you can just rejoin with the same link you used to join the meeting. All right, I'll start with a brief introduction of myself. My name is Hilary Wonko. Um, I'm a blockchain community manager. Got to learn about crypto around 2017. A friend sent me some Bitcoin and used it for some transactions. Then I got involved in um, trading Bitcoin peer to peer. Somebody sends you Naira and send them back Bitcoin for if they want to use for some transactions online and stuff like that. And over time, I got to learn more about crypto. Someone introduced me to Ethereum. From there, it just blew up. Everything. I went down that rabbit hole, and it's just been an exciting ride learning about blockchain technology and decentralization as a whole. Um, so currently, working as a community manager at a PR and marketing firm called Amazix, and there I help to manage some cryptocurrency blockchain communities. And I'm also personally involved in helping a few communities and investing in a few projects. So generally, it's just one thing or the other in the blockchain space. So one of the reasons why I'm passionate about blockchain technology and decentralization is how it opens up access. How it opens up access. People have access to this technology. People can use this technology. People can transact on the blockchain or send cryptocurrencies from one place to another without restrictions. They can, without restrictions. There's not one central body or organization that's controlling everything and gatekeeping this access to cryptocurrencies and being able to transact. So and that open nature, anybody can come and make their contributions and build because of the open source nature of blockchain technology and how most cryptocurrencies are built. So that got me. That was one of the things that got me excited when Sonia reached out to me about IPFS. I had heard of IPFS before, but I didn't really pay much attention to it. Sometimes I collect NFTs. I don't know if any of you know about non-fungible tokens on the blockchain, and I know some of them have their metadata or the images stored on IPFS. So that's how I know about. That's like the only thing I knew about IPFS before Sonia talked to me about it. And I was like, wow, this is interesting. I have to look into it. She sent me this table with a long list of use cases, and I was like, wow, my mind was blown. I was like, IPFS is, if the way to think about IPFS is to think about it as the web. You understand? Whatever you can build on the web, the way the web is built now is same things you can build and bring onto IPFS and build on IPFS. The main difference here is decentralization and the open access. Okay, so we can build a true decentralized web on IPFS. I like to do this one line definition of IPFS that I liked from one of the IPFS docs. Let me see if I can get it here. Okay, it says IPFS is a distributed system for storing and accessing files, websites, applications, and data. So when you think about it, like, it's a very simple definition, but it's also powerful because you can see how much possibility there is with building on IPFS. And another aspect of IPFS that I'm really excited about is the community, because when you consider like the basic IPFS infrastructure, it's basically people storing and then making files and giving access to files. It's a distributed file sharing system. So I can have a copy of the file or part of that file, and somebody else has it, and it's just distributed globally. And each person that needs access to these files can come, and then these files are made available to them from each of these nodes that are hosting these files. So another important aspect of IPFS is the community and the participation that is involved in it. So each of us here will be part of this community. Each of us here will be part of building on IPFS, and each of us here will be part of using applications that are built on IPFS. And those are like the three major points or pillars or goals that we'll be looking at as the IPFS Africa community. The first thing is to get as many people as possible, as many of us as possible, to start building core applications on IPFS. To start building as many applications as possible on IPFS, and then getting getting end users to use those applications, getting other people to use those applications, and then getting as many people as possible to host nodes on as many people as possible in Africa to host nodes on IPFS for IPFS. So those are like the three major, most important goals that we're looking at, things to achieve as a community. So we'll be looking at holding more meetups like this, holding workshops, more technical workshops that can get more of us involved, more of us building on IPFS, more of us aware of this technology, and then we'll see where that goes. We'll build a strong community here, and we'll see where that goes. And in exploring IPFS, there's endless, like I said earlier, there's endless use cases and application areas, and those things we'll be exploring during this talk here. And then the open source nature of IPFS means that anybody can come in and contribute wherever you find that your area of expertise, wherever you want to learn also, because it's not just for developers who are experienced, but for those of us who are still coming in and learning about tech, even if it's just front end, you understand, you can start working with IPFS, you can start building on IPFS, and then the community participation, you understand, every one of us can, even if you're just an enthusiast and you're not a dev yet, you can get the word out there, you can use the apps that are built on IPFS, and you can contribute to the community somehow. And there's space and there's enough opportunities for participation and networking for each and every one of us, because we'll also be meeting some wonderful and interesting people as part of the community here, and each of us will work together towards growing the community. So like I said earlier, we're on a limited plan for Zoom here, so it's possible that at some point the meeting might cut off. So you can use the link that you received to join the meeting to join in again. And then after talking now, I'll introduce Sonia, who will introduce IPFS to us, who will share more about IPFS to us, how to get started with IPFS, the use cases, and how to start building on IPFS. So I guess that's it. And after this, now we'll have a Q&A session. Yes, very important. We'll have a Q&A session. So while you listen, please make sure that you have your questions ready. We'll be taking your questions, and we'll get to answer all the questions you have around decentralization and IPFS. So I think now Sonia you'll be able to take the stage and
yeah, sure. Thank you so much, Hilary, and thank you for the great introduction to your developer story and how you got into Web3. I think all of us share the uniqueness of our story in the sense that the blockchain industry is so large that most of us have found our way to it through very many different ways. And that's the reason why I think everyone here will also end up having such an amazing story, because once you get inside the world of blockchain, inside the world of decentralized technology, you pretty much find yourself in a very interesting space with a lot of very interesting goals and objectives. So thank you very much. So just to get us started on what IPFS is, I'm going to share a simple presentation here on pretty much getting started with IPFS. Just a brief introduction about myself. Here, wait a second, let me just do this. Let me do this so that I can see some bandwidth and we can go through. The presentation. Awesome. All right, yeah, so a brief introduction about myself. I am a blockchain developer. I have been in this space since early 2016 when I was first introduced to Bitcoin, Ethereum, and IPFS. And since learning about decentralized technology and distributed technology, I have pretty much made it a goal of mine to create an environment or a space where a lot of us developers who are interested in this kind of technology could come together to build all of these solutions and applications. So far, I have worked on several kinds of applications, including Playmaker, which was a sports ticketing solution that was going to be built off of a fork of the VeChain code base. And I also worked on a distributed e-commerce platform that was going to be built using some type of masternodes. And these are things that you will eventually learn about as we go along. And I'm also a conventional technical writer, and I write about subjects ranging from distributed technology to open source software and even tech education. And I also currently still with the IPFS Africa community. And like Hilary mentioned, we have certain goals that we hope to achieve with this community, namely increasing the number of applications that are built from the continent, increasing the number of nodes that are hosted on the continent, and then increasing the number of end users who use IPFS-based applications. And the way that we can get to that is to first understand why the internet is very vital to the solutions that we've built. And that's because most of us can agree that the internet has become one of humanity's most important technology. I mean, we use it to shop, to pay bills, for entertainment, and it would certainly cause anxiety to so many people if the internet were suddenly shut down. And yet the way that we use it today, it's just a collection of centralized institutions that are acting as clearing agents for internet users. What the expansion of the internet and the consequential centralization of the web itself has done is that it has exposed a lot of the limitations in this kind of system architecture where, for example, you find a user's access to the internet is at the mercy of their provider. And CEOs of large tech companies often turn the companies that they built into gatekeepers of information. And something else that you probably have also noticed, if you're an avid internet user, is that most of the platforms that we use have created terms of service or data policies that require users to agree to the collection of their own personal data that is then monetized by third parties. Now we can go into a lot of details into all the different ways that these kinds of limitations have affected the quality of the internet itself today. But the main point that you can kind of take away from the limitations of centralization is that this architecture of centralized servers becomes a single point of failure, where if they fail, then the websites and applications that depend on them also fail. If you're keeping up with a lot of tech news, you'll know that in the last 48 hours, a lot of Google services went down. And the reason such an outage can happen is because of this centralized nature of server systems. On distributed solutions like IPFS and other third wave internet solutions like Ethereum and Bitcoin and IPFS and Golem and so many other Web3 type applications, is that it's enabling not just read and write capabilities on the internet, but there is availability, there is data verifiability, and there's also components of trust built into these solutions themselves. Now, these are tenets that we will look into as we analyze IPFS in depth. But what you can see from this illustration is that the internet as we use it today in its Web 2 format only allows for people to interact with data on the web um, by reading and writing. So you provide content, and then then you get content that's already been written. But with Web3, this, the solution itself, the technology itself is built on certain values like the freedom of speech, freedom of assembly, uh, user control of their own data, privacy, dependable infrastructure, and even self-sovereignty. And this is reflected in secure self-publishing, secure communication, secure storage, verifiable transactions, and trustless infrastructure. Put together, what you're able to do with this kind of solutions like IPFS is you're able to build tools that can help you bypass censorship, internet shutdowns, and even surveillance to some extent, because then you don't get to use solutions that have inbuilt trackers. You can manage to use, you can still manage to access information and to share information even when there's systematic shutdowns, say with your internet service providers, or even just basic censorship where platforms do not allow access to certain kind of content based on decentralized authority that's running the solution. So then, what is IPFS? I think Hillary gave us a really good definition of what IPFS is. And the way that I also like to describe it is that it's just a synthesis of multiple peer-to-peer systems that are designed to create a distributed and content addressable file sharing and storing protocol. And essentially, that's just making the web work peer-to-peer. And one of the ways that it does this is through the content addressing model. Um, See, on the traditional web, that is HTTP, which is illustrated here, example.com is the location for the return data bus.png, or yet on IPFS, the contents are returned using the content identifier, which is this cryptographic hash, which is calculated from the content itself. And then the returned value becomes the address of the data. And one of the things that we have observed as benefits of using this kind of content addressing as opposed to location addressing is that one, data is never lost as long as a valid copy of a file exists. Then this data is never lost. Say, if I was to upload this image, vast.png, to a website, example.com, and the server that is hosting example.com were to go off, then I will never be able to retrieve my image. Meanwhile, on the IPFS network, because it's peer-to-peer, if I add my image to the IPFS network, and a copy is stored on each of these nodes, so each of these routers represents a node on the IPFS network. If each of these nodes was to save a valid copy of my file, bas.png, then if one or two or more than half the servers go down, as long as a valid copy exists on the remaining servers, then my data is still available on the network. And what content addressing also implicates to do with data is that data integrity is maintained because these cryptographic hashes act as a data's fingerprint, which provides validation that is not available on location-based address systems. What I mean by this is, for example, if someone went to my server where my image bars.png is and changed the image, say, from a cat to a dog, and still renamed the image bars.png, the server will not be able to tell the difference that the content has changed. But on the IPFS network, because the cryptographic hash is derived from the content itself, if I was to change one word or two words or change the image, then the cryptographic hash is changed as well. And that data will now be marked as modified. So it will have to change the cryptographic hash, which will also mean that if someone was to request the same data and it was changed, they would have to get the new link or the new cryptographic hash to find the new content that they're looking for. And because links do not lie, IPFS links permanently point to their content. So if I had a picture of a cat and it's the same cat, even if it's uploaded by multiple nodes, it will return the same link. Now, the way that the IPFS network is able to do all of this is by integrating a stack of subprotocols, which are responsible for different functionalities within the network. And I can start you off by describing what each of these subprotocols are on a high level and what they do on the network. So DHTs, or distributed hash tables, is a subprotocol that's used on the IPFS network to allow nodes to keep track or to find other peers on the network. Now, because this is a peer-to-peer network, The network needs a system or a function that is able to keep track of the number of peers that are on the network, to keep track of the data blocks that are in all of these peers, and then to retrieve these objects when a request is made, given that if the associated keys are shared. So keys in this instance is what the cryptograph is, the hashes that are generated every time a file or an object is added to the IPFS network. Merkle DAGs, or directed acyclic graphs, is a self-verified structure of a map or a tree of all the network objects that are cryptographically linked using content identifiers. Okay, okay. Let me see if I can get a really good description of what this looks like. Just a minute. All right. So this so I was trying to describe what a Merkle DAG or distributed acyclic graph is on the IPFS network. And the easiest way to explain it is when an object is added to the IPFS network, it is chunked into smaller parts. Each part is about 250K, and then each part is hashed. And hashing is the process of getting, hashing is the process of getting a cryptographic address of any object that's added to the network. The default cryptographic algorithm that is used in IPFS to generate content identifiers, that is the SHA-256 string, is what's called cryptographic hashing. It's the process. So when each part of a chunk is hashed, a CID is created for a chunk, and then these chunks are combined into a hierarchical data structure for which a single base CID is computed. So this is a graph, for example, of a node E, which contains reference to the hash of a node F. And I am still trying to okay, I'm hoping all of you can see this. This is what we call a DAG built-in visualizer. And it's just a simple tool that was created to kind of help break down the process um, of hashing as it happens on the IPFS network. And what I will demonstrate here briefly is how the chunking process happens. And chunking is the breaking up of um, objects into the size of 256. But what you can see here is you can chunk at any size that you want. So if you want your object to be broken up into different sizes, you can specify here. And what UnixFS is a file system that's used on IPFS to kind of link different kinds of objects across different nodes. And then we also have the distributed acyclic graph formats here. And the best way I can demonstrate this is by adding, so we're going to add an object to the IPFS network right now. When I say upload this image to the IPFS network, you can notice that we're connected to the IPFS network from our browser. And this is possible because they used the JS implementation of IPFS, which is a great implementation for using when you're building solutions that are going to be browser-based, that are going to be accessed, say, from desktop or just pretty much any type of browser. I think we'll talk about that in more detail as we go along. So here, can everybody see? Just let me see the chat if everyone can see this. Just say yes if you can. Okay, awesome, awesome. So what this is a Merkle tree. And what it is illustrating is the object that we've added to the network. This is the CID, the content identifier that was generated for this image. So if I was to search IPFS for this image, I would find it at this address. So the cryptographic hash that's generated becomes the cryptographic hash that is generated then becomes the CI, the address of the object itself. Now, if I wanted this chunked into bigger pieces, say 16,000 bytes, then the leaves that are generated is just the two leaves, which is split into two different nodes, which is what we were trying to describe here. Now, if we imagine it and run, say, directory E through a hashing algorithm, which contains the subdirectories F and G, then the content derived hash we will get back will include references to these two directories because they have a chunk of the information that builds into node E. So the root CID hash is unique to a tree because it contains every node all the way down. And these data structures are built backwards from the leaf nodes up to the root node. And the way that I can describe that again is here. Say if I was to make it smaller chunks, and then I could make it food for children max. What all these are the leaves, the leaf nodes that will be referenced in the root CID. So the root CID here has references to all of these nodes because they all have a chunk which is 1024 bytes of the final image. Now, the third subprotocol that is powering the IPFS network is BitSwap, which is a BitTorrent-inspired protocol that distributes data on the network using a block butter exchange process. Simply put, on the network, um, the DAGs, the decentralized acyclic graphs, can detect. No, actually, what the what the block data exchange process, actually, how it actually works is a peer or a node or two nodes that are in the data marketplace will come each with a want list or a have list, and what these are is just a list of blocks that they want, say information request, or a list of blocks or objects or information that they want to exchange. And what the protocol does, BitSwap, is facilitate this process of exchanging data on the IPFS network itself. Now you learn about most of these concepts in depth once we start doing an exploration series of IPFS, where we'll go into a lot of this in details so that we can actually have code examples for us to actually see how they all run. For the Merkle DAGs, we already did a session on decentralized data structures that goes into a lot of depth about how the Merkle DAGs work. I think we can find a link for that and share it with you guys so that you can have a look. So for now, I'll just run through the rest of the subprotocols so that we don't end up spending a lot of time here. Now, IPLD as a subprotocol on IPFS stands for Interplanetary Linked Data. And this is a hash link data structure that models its output for a linked object with a data block. Say, if you're familiar with how metadata works on the web currently, is that a portion of a data of a data structure will have metadata descriptions like the name of the object, the size of the object, the location where the object was first shared, etc. Now, all of that process is facilitated on the IPFS network using the interplanetary linked data subprotocol, so that every time an object is added to the IPFS network, the subprotocol will start tracking all of the metadata related to the object that's added at any given time. And then IPNS is the interplanetary naming system for IPFS, and this is actually a very interesting technology, because if you're familiar with how websites, servers are currently named on the internet, you know that it can be very easy or very hard to find certain kinds of domain names. Sometimes you can buy a domain name, but then the host server, for example, will crash and our website is suddenly not available. Say, for example, you like to visit a site called www.ilovethisite.com, and then one day you go visit the site and say it's changed. It's no longer the site that it was, say, 24 hours ago. So the content has changed. Sometimes you find the site is not available. There's a 404 error. There's all kinds of problems that you can experience with trying to access certain kinds of domains on the internet right now. But because IPFS works, the way that IPFS is designed to work makes it that any kind of data that is added on the network is permanently available on the internet. You can assign them domain names that are also permanent. domain names that will never get taken down, domain names that will never go offline, because as long as the data that is attached to it is on the IPFS network, then the data will be available on the internet forever. So IPNS is a naming system on IPFS that is designed to give permanent domain names to IPFS objects, to IPFS addresses, and to IPFS applications. There's also a lot of other decentralized naming systems available that have been developed. There's domain names available from unstoppable domains like .crypto domain sites or .zil. Ethereum is also working with this decentralized naming system that is the ETH or .eth, which also functions as a wallet for people to send and receive money from the domain name as well. So again, these are still things that we'll talk about in more detail as we try to learn more about all these different aspects of distributed technology and IPFS specifically. So libp2p is a library, is the library that's actually running most of the IPFS network. So it manages functions like peer routing, content routing, communication, and it may be one of the most vital subprotocols that is being developed by the protocol labs, and it has been used in so many other technologies just beyond IPFS itself that they had to continue developing it as a separate technology outside of IPFS, and it's also one of the main overlay protocols that's being used in the latest release of the Ethereum network. So perhaps the next session that we will do will be a link P2P session, so that once you understand how these core functions of the IPFS network work, then we can go into the other subprotocols. Let me know in the chat if you think that's where you would like us to get started with an Explore IPFS series. File systems is the last subprotocol on IPFS. Of course, I think it would have been very, very difficult to build a distributed network that works with distributed data systems, data structures, without building in a file system. And on the IPFS network is not different. We have several types of file systems. We have mutable file systems. We have immutable file systems, and then we have unique FS file systems. And all of these are different in the sense that some of these file systems can be modified in the sense that you can make edits and the network can make provisions for those edits to actually be handled well within the network. And then there's immutable file systems, which is the default on the IPFS network. And here, files cannot be changed without changing the hash of the object itself. So again, this is something we will also be covering in depth once we start doing an in-depth IPFS exploration series. But for now, I think we can go into what the current implementations of IPFS are for someone who just wants to get started. And the two main implementations of IPFS for users service right now are Go IPFS, which is currently available on version 0.7.0, and JS IPFS, which is available at version 0.52.3 as of 3 hours ago. There's also other implementations in Rust currently being developed and being tested. If you're a Rust developer and it's something that you like playing around to kind of discover new things, you can always head to the Rust IPFS GitHub repo and see if you can start contributing. But what are the main differences between these current two implementations, and how do you determine as a new user where you should start from? Well, we've seen a number of nodes. The number of nodes that are running, that are using Go IPFS, I think has been increasing 10 times over the months in the last 1 year. And this is ideal because Go IPFS is great if you're building solutions that run on big data sets, and it also has several advanced features like file store, private networks. So these are like IPFS clusters that you can build, say, for example, a private network on. Say you want to build a solution that has data privacy sensitivities, and you do not want to share your data on all the IPFS nodes. Then you could just create a private network on IPFS cluster of nodes that is just built and running to store and to share private data between the selected nodes, between the accepted nodes. Um, there's also uh, relays and tunneling features available on Go IPFS and the quick transports, which is the default now as of the latest Go IPFS update. On JS IPFS, on the other hand, like I had mentioned earlier, when I was demonstrating the DAG builder, is that it is flexible and it is ideal for browser-based applications, because you're able to incorporate web workers, service workers. So these are just nodes that are available 24/7 to send information between a request that's made on a browser and the IPFS network. Then if you're building, for example, a platform that's based on IPFS and it will be available on the browser, then working with JS IPFS is ideal for you. And the implementation of both incorporate the core IPFS protocol itself, that is the core API. They both use the TCP and WebSockets as the main transports for communication. And they both have built-in distributed hash table subprotocols, which, like I mentioned, is what ensures that peers are able to communicate with each other, and peers are able to send and retrieve objects from one another using the BitSwap protocol in the data marketplace. This table, for example, illustrates how one of the features, that is transports, vary in implementation between between JS IPFS and Go IPFS implementations. The link P2P interface transports, for example, is just one of the many subprotocol modules that is deployed on both implementations. And you'll see that on Go, most of these transports, that's TCP, WebSockets, WebRTC, and Quick, are all built into the implementation. But in the last few months, there's been a lot going on with the depreciation of SECIO as an encryption protocol. And the new protocol for data encryption, that is the noise encryption protocol, has been implemented on both JS and Go IPFS. So regardless of whether you're using either of these implementations, then you guarantee the availability to, say, encrypt your data before you add it to the network. This is just one example of how this almost parallel development ensures that whether you're using JS or Go for your application, that you will get all the features and full implementation of the IPFS protocol. Now, there's several ways to get started with IPFS, and from the way that I described both of the implementations, um, if you're impartial to say working with Go IPFS, you could install Go IPFS and run your own node. You can also use any of the APIs currently available. The core API, which you can then embed into an application, and your application will run on IPFS. You can also use the client API or the HTTP client API, and I'll get all of these links and we can have them shared with you on the chat. And then we'll also do a brief demonstration of how to actually install an IPFS node. If that's something you want to see, just let me know. Now, all of these options are also all available on JS IPFS, and the corresponding links will also be shared on the chat. So the JS Core API is just a package with all the Core API information that you can link or add to your application, and then this is where the service worker nodes and the web worker nodes come in handy to help you actually retrieve data from IPFS directly from the browser. And as you can tell, this solution is very popular because a lot of applications are still on their test mode. So a lot of them are being built as browser-first solutions. And as of today, the HTTP gateway is being used to make nearly 30 million data requests a day. And in the last 6 months alone, I think that number has gone from 2 billion to maybe 2 billion terabytes of data being requested from the IPFS network. So the use of service worker nodes to retrieve information from the IPFS network is definitely one of the easiest ways to get started. And the links to getting started with that are obviously here, and we'll have them all shared with you. Yeah, in fact, they'll also be shared on the Slack channel, so I think Hillary will also share a link to that. Yeah, so like I was mentioning, there are other ways of using IPFS as well, including on your browser, like the Opera Mini browser, if that's your browser of choice, or the Brave browser. All of these different browsers have made the resolution of IPFS-based addresses on their browsers very easy. And if you already have a website and you just wanted to see added to the IPFS network, there's also a lot of other solutions that are available for that, like Fleek, which is a service built on IPFS to help you deploy your websites in 10 minutes or less. And if you have a website, you have a domain, you've added it to the IPFS network, and now you want to add a permanent domain to your website, then the solutions like the Ethereum name service or the unstoppable domain service, which I had already touched on earlier, to give your permanent applications permanent addresses. Now, the IPFS ecosystem, since development started on this technology, has been incredible. I think every year we see all different kinds of solutions being built. These people building tools, services, data sets, different kinds of projects using IPFS. And this slide here is just a small representation because the ecosystem is always growing and there's still even more opportunities for more of us to build even more solutions. And that's one of the goals of having an IPFS Africa community is to have more and more of this ecosystem solutions coming from this continent. And the opportunities can cover all different kinds of areas. Say if you just want to build network infrastructure, if you're a developer and you have an idea of developer tools that you can build on IPFS or for other IPFS developers, if you have ideas of the kinds of private network diagnostics that can be built on the IPFS network, um, you know, any ideas that require the use of large data pipelines or data management solutions like um, storing and distributing front-end applications and user data. All of these are very many opportunities and even more than we can even think about. You know, you might have ideas that even we haven't thought about of what you can build on IPFS. And what we want to do is to support that process for each and every one of you. And the way that we want to do that is to have several events like this that will, for example, explore IPFS in depth. We will host hackathons to see what kind of ideas we can come up as solutions. We're just brainstorming kinds of applications that we can build here, and then try to pull the kind of resources that we would need to actually build this application. And the way that we're going to do that is around community itself. And we have very many ways that you can stay in touch with the community to see how you can participate, to see how you can add your contributions, because we want to build this as an open place to accept all kinds of contributions from all over the place. So if you want interactive tutorials, they're available on Proto School. If you just want to discuss IPFS, there's a forum on discussipfs.io. If you want the list of resources for how to get started, we have a repo for that. All of these links will be shared with you on the chat, and we will also share all of these links and this presentation on the IPFS Africa Slack channel. So if you haven't already joined, I think Hillary will share the link for that now, and then you can all join us there, because I think we're going to continue this conversation, and we want all of you to be there as well. So I don't know if there's any questions, Hillary. That's my presentation for now.
Okay, thank you very much for the presentation. I learned a lot. There was so much information there, and I just posted the link to the Slack channel now in the chat. And we have a few questions, Sonia. So we can take the questions now, right?
Yes.
Okay. So the first question we have here from Henry, when you were discussing the Merkle DAGs and demonstrating, he was asking the maximum chunk size, is it 26214 or 262144? I didn't get that. So if you can show the screen again for that, and then we'll see what it is.
Sure, just 1 second. Let me share my screen again so that So these are the chunk sizes. They start off at 32 bytes, and the biggest is a rabbit, which comes to about 40,000 bytes per chunk. Um, the way you could demonstrate the difference in the chunking process, again, I will just add the same image that I added before. It will generate the same CID, the same content, um, and this is the size of the node if it's at its largest. And if it's at its smallest, then the Merkle tree becomes a huge forest with multiple leaves. I think the leaves will be either between 200 to 300 leaves because this is the smallest chunk. And remember, each chunk has to have its own content address. Each chunk has to be hashed individually before it is added to the network and stored to the network. So if you're adding, for example, really huge um, objects to the network, then it is always what the network will do is that it will determine the best cryptographic hash to use to chunk each of the data so that it can find the most optimum size of the chunks itself. Now this is taking so long. We're gonna try another size, see if that helps. What this process is doing is the cryptographic hashing process where each chunk is being hashed individually and a content identifier is being generated for each. So what these are called trees. Node or okay, so these are called branches, and these are called the leaves. Where'd you go? Why? And what it represents is essentially a Merkle tree of all the nodes that carry the representative um, content identifier of, oh, I don't know if you can see this. This was at its smallest. So this becomes a forest essentially because as opposed to having just one node, then you have a whole tree of them, as opposed to having two leaf nodes and two branches. You end up having more branches and more leaves and more nodes. So the cryptographic hashing process chooses the best algorithm for every object that's added to determine the best optimal size so that it doesn't spend a lot of size in each node that it runs. I don't know if I answered the question. But
Yeah, I think you did.
I'm feeling like if I keep talking, I'll keep going.
Okay, we have this question here from Peter. He says IPNS versus ENS.
Ah, that's a good one because IPFS is still under development. It still has some challenges that are currently not available on ENS, which, for example, it's very slow to retrieve data from the IPFS network using IPNS. But as more development improves, I'm guessing that all the capabilities that are currently available on ENS will also be available on IPNS. But what I generally advise in the meantime is you can find other solutions like unstoppable domains, which is way ahead in its development schedule, and you can use it both as an address for your content and as a wallet so that you can send and receive money using your unstoppable domains domain as well.
Okay, so unstoppable domains is like a very good alternative. Has um, it's more developed than the IPNS protocol.
Yes, I think
Sub
that,
protocol. Yeah.
yes, yes.
Okay. Okay. Can the IP? This is from Eva. He says, can the IPFS network work without the presence of any of these sub protocols?
It can, but it will be
Like,
very difficult because
okay.
each of the subprotocols carries a different function, right? And these are all functions that are critical for the running of the network itself. Say, for example, if you have libp2p, which manages content routing, and content routing is basically ensuring that this data gets to where it's supposed to be, or this peer communicates with who they're supposed to communicate with. So if you had libp2p, but you didn't have, say, the distributed hash tables, which keeps track of all the number of peers that are connected to another peer and keeps a list of all the objects that are added on the network, or if there was no Merkle DAG, which is the data structure that tracks all the nodes that actually um, build up a data structure, then the whole network falls apart. So all of these different subprotocols are being developed and improved all the time. This tightening in some of these pub subprotocols to ensure that things like hacking don't happen. Um, and the reason for that is once each of these different subprotocols is built to its absolute max efficiency, then the network will be able to run seamlessly. So no, there's
Yeah.
absolutely no way for the network to run if one of these was missing.
Yeah. Makes sense. Okay.
Yeah.
So he's asking, does it mean that he can build a website using IPFS? That he can build an entire website on IPFS?
Yes. Yes, you can. We have websites that are being built. We have applications that are being built. All types of tools that are being built in IPFS as well. I showed you
Yeah.
a slide with all the different um, ecosystem solutions. And what I
Mm.
also recommend is checking out Awesome IPFS, which is a website that lists all the different solutions that have already been built on IPFS. And you can also check out the different use cases for applications
Yeah.
that have been built so that you can have an idea of what the IPFS network can essentially do, which is very little. There's very little the network cannot manage.
Cannot manage. Yeah. Okay.
Yeah.
We have this question from Crispy. It says, "What is the guarantee that data stored is safe for life? And is the network hack proof?" He's also asking this coming from the angle of NFTs and storing NFT data or images and metadata on IPFS. So is it safe for life? Is the data stored on IPFS safe for life? And is it hack proof?
Yeah, so those are two very good questions. Um, is the IPFS network the permanent web? How do you ensure that? And the way that the network ensures that is by the use of cryptographic algorithms that are built into the network itself, which then um, ensure that data integrity is maintained. And the way that these algorithms work, cryptographic hashing is the process of taking an object, chunking it, and then running it through a hashing algorithm, which in the default in the IPFS network is the SHA-256 algorithm, which then outputs a string, a 256 string, which becomes the hash of the object. And then it is based on the object itself, and it becomes the address of the object itself. So if one of these three things was to change, then the hash will change. So if you changed an object, then the hash will change. If you changed, for example, the content of the object, which is what I'm saying. So for example, if I was to save an object, the image of a cat, and oh, wait, I can demonstrate this. Just a minute.
Yeah.
So this is an image that we added on the IPFS network. And this is its hash. If I was to add the same image on the IPFS network, what I would do is, okay, I'll start again with a new kind of image so that I can ask you to note. All right, let's do that. So I'm going to ask you to note the CID of this image. This is the content identifier of the image that we've just uploaded. If you've noted it, I'm going to try to upload the same image and you will see whether its CID changes or remains the same. So that's the same image. And if you'll notice, you'll see that the content identifier for the images remain the same. And that's because once an object is added to the IPFS network, it is there permanently. And the only way that its address can change is if I alter the image. Say I went to the image itself and I cropped it, then its content identifier will change. If someone else in any other part of the world was to add the same image on the IPFS network, what the cryptographic hashing algorithm will do is that it will determine that this is the same image that was uploaded on this node so and so days ago. So it will give him the same content identifier because a valid copy of it will exist on every node on the IPFS network. So that is how data becomes available on the IPFS network permanently. Now, if someone wanted to hack this, for example, this image and say they wanted to alter it, they wanted to maybe steal it because you cannot delete objects that have been added to the IPFS network. You can only try to modify it. But if they try to modify it, what will happen is the content identifier will change and anyone who has the original or valid copy of this object will know that there's another object from this object that was modified. So that makes it essentially permanent and hack-proof.
Makes sense. Makes sense. That makes sense. And I think it also ties into this question from Henry here. He says, is there any means in place to regulate the quality, authenticity, of information or files that get uploaded on IPFS as a form of security for users querying the network? And I think that answers it also quite well. Or unless you want to like elaborate further on that.
Yeah, no. The only regulation say is if you're going for say if you're working with sensitive information, if you're working with private information, then of course there's sub-protocols like the noise encryption, the noise encryption protocol that you can use to encrypt your data before you add it on the IPFS network. You can use private networks if you're working with sensitive data that you do not want to be available on the wider IPFS network. But again, if you're talking about alterations being made on data, or if you're talking about the policing of the kind of information that is added to the network, then no, those two options are not available on the network.
Okay. We have another question here from Crispy. He says, how fast is IPFS when it comes to, I think he means like downloading or sharing information? Like how fast is it and gets a request in real time or querying the network?
Yeah, no, that's a really great question. Now, DHT and BitSwap improvements on the IPFS network is kind of a rolling theme every update. And I think up until this point, The core development teams have been really trying to push updates almost every 2 weeks. And a lot of the content routing improvements on the IPFS network provide for faster download speeds. I think there's something I can share about this because we were at the IPFS meetup last week and we got some pretty amazing stats about this. Let me just find them. So these are the DHT find times on the IPFS on the Go and on the JS and Go implementations of IPFS as of the last release. And what you'll find here is IPFS at version 0.4.3, it was taking the network about 50 seconds to find information and reroute it and route it successfully to the requesting node. But over time, as you'll see with zero point 0.5, the find speeds were reducing from 5.4 to 3.8, and right now with version 0.7, the content routing speed is about 1.5 seconds, and it is rated at 100% successful. And what that means is with every improvement that the IPFS network is finding and retrieving the information faster and faster.
Okay, that makes sense. Thank you very much. Peter is asking again, when dealing with big data, how does this affect speed? When dealing with big data, how does it affect speed, data integrity, and design complexities when integrating it that's a decentralized application?
Yeah, great question. And I think this was one of the main challenges that was identified with Lib2P and why a lot of the hardening has been going on with the sub protocol. And even which also led into the development of Filecoin, which is a data storage protocol that essentially is built on top of IPFS to enable users who are working with large data to use a platform that is specifically for storing data. See, IPFS was essentially developed as a file sharing protocol, which made a lot of the emphases in the development were regarding file sharing. But as the need to store large data sets and large data grew over the network, then the creation of Filecoin pretty much ensured that people who were unable to work with large data on the IPFS network could easily migrate into the Filecoin network, which is built more sufficiently to deal with large data solutions and other large data set solutions. So we can also do a session on Filecoin for people who are interested in that aspect of distributed file storage. Just let me know if that's a thing that you would all be interested in.
Okay. Um, Crispy is asking for us to give him permission to leave. Yeah, Crispy, thank you for spending the time with us. So
Yes,
have a great day. I think I'll post the link to the Slack channel here so you can join us there again, and then we'll chat some more on Slack. Thank Crispy.
thank you,
I think
Crispy.
that's all for the questions. Yeah, I think that's all the questions we have for now. If there are any questions, please feel free to send them Okay, it says, will users, Henry is asking now, will users get incentivized if the data they uploaded provides query results? I'm not sure if I
So
got that
far,
question right here.
I think I understand the question. And
Okay.
so far, there's no model around incentivized query results because a lot of the data that is being shared within the ecosystem again relies on the use of distributed decentralized domains and then the use of actual um, addresses to find data on the network. Because a lot of the links that we're still using on the decentralized web are not human friendly. You can't just tell someone to go to google.com to find out what information you want to share with them. You have to give them a 256 string of an address to the content itself. Then a lot of those systems for providing incentives to query results have not yet been built. But that is something that you can always look into. There's people who are trying to build search engines on the IPFS network. So you can check what they're building and see if that's something that can be built into the search engines that they're developing.
Okay. Pete says he's interested, definitely interested in learning more about storage as well as the new incentives for miners to charge for storage. So maybe down the line we could organize a session for Filecoin for those who might be interested.
Oh yeah, awesome. And in the meantime, we can start a channel on the Slack for Filecoin, and then we can have all Filecoin related discussions there.
Yeah,
Yeah.
yeah. Okay, I think that's it for all the questions we have here. I don't think I'm missing anyone, so
Oh, that's awesome. Thank you guys so much for
yeah.
joining. Thank you for all the questions. I would definitely love to continue these conversations. I know we're all heading into the holiday, but if we could get some of these events going on as soon as we start the new year, it would be awesome. And I can't wait for you guys to just come up with ideas that we can start marinating on and working on in 2021.
Yeah, I'm looking forward to 2021. It's going to be a great year, and there'll be a lot of learning and building for the IPFS Africa community. Yeah,
Yes. Oh, that's awesome. Okay,
yeah.
fantastic. Well, thanks for joining, guys. I'll see you on the Slack. Thanks, Victoria. Thank you, Peter, Henry, everyone.
Thank you,
See you on the
everyone.
Slack. All
Yeah.
right.